I'm waiting. So first speaker of the afternoon session is Professor Rubens Lichtenthäler. Maybe there are many German people, so you feel familiar. So title is Selected Ongoing Project at RIBRAS. Please start.
Okay, thank you. So I'd like to thank Gaston Krein for the invitation to present this talk. Actually, this is the second talk in the same subject, as Eileen on Monday presented a very complete talk about RIBRAS. But in any case, I will try to present some novelties. So this is a scheme of our laboratory. This is a pelletron accelerator of 8 megavolts. It's a vertical machine, and then here you have 6 beam lines. In one of these beam lines is RIBRAS installed. So RIBRAS consists of 2 superconductor solenoids, which are here. This is one, and this is the other one. And the beam line where we have 3 scattering chambers, the primary scattering chamber, a midway scattering chamber in between the 2 solenoids, and a secondary scattering chamber after the second solenoid. So the RIBRAS uses the in-flight method to produce secondary beams of unstable particles. So the primary beam is produced by the pelletron accelerator, and usually is lithium 6, lithium 7, or boron. It comes from the left and collides with the primary target, which is inside chamber 1. Primary target usually is a beryllium foil, but can be also gas target and everything. So in-flight method means that the primary target is thin, in the sense that the primary beam punches through the target and continues its way, and the secondary particles are produced here and are accepted by the solenoid. The selection is a B-row selection. It's a magnetic rigidity selection. So here you can see every important component of this system. One is primary target. 3 is a Faraday cap to suppress the primary beam. So it's important to say that the primary beam has about 10 to 13 particles per second, whereas the secondary beam has about 10 to the 5, 10 to the 6. So it's important to completely suppress the primary beam. So this is the function of this number 3, which is the Faraday cap. And then there is a collimator to define the acceptance angle. The acceptance is between 2 and 6 degrees. So the particles are produced here and are focused in a position in the central chamber, chamber 2. And around this position, we may have detectors. And in addition, we have these blockers and collimators to suppress unwanted secondary beams. So this is a list of some of the secondary beams that we produce. Here is the secondary beam particle. Here is the reaction. So as you can see, the primary beam, the target, and here the secondary particle, the reaction Q value. Most of these reactions are transfer reactions. And this is the intensity that we actually have in RIBRAS. You can see it's between 10 to the 4 and 10 to the 6 particles per second. And this is the energy resolution of the secondary beam. So you'll see that you usually have beryllium 9 as target. With beryllium 9 and lithium 7, you can produce helium 6, but also lithium 8. But we can also have gas targets like helium 3 to produce boron 8 and beryllium 7 beams. and several other combinations that can try to produce secondary beams. So, this is a profile of the secondary beam spot in the central chamber. So this was obtained, it was a PPAC. PPAC is an XY detector. So he gives the position, a cut of the transversal cut of the beam. So you can see this spot. This is the spot size of the secondary beam, which is of the order of 4 to 5 millimeters. This is an identification spectrum corresponding to the previous slide. So here you have what we use here is a telescope. Telescope is a set of 2 detectors, one thin detector and one thick detector. So the particle punched to the thin detector leaves a certain signal, which is proportional to the z-square of the particle, and finally it is stopped in the E detector. So here you have the signal from delta E and signal from E detector. So it's this kind of identification. You can separate different particles. Particles with the same Z fall in the region in a cut like that. So here you have lithium 7. Here a little bit above you have lithium 8, helium 6, alphas, and lighter particles. So the resolution of our secondary beam is, for the case of lithium 8, is of about 500 keV. Here I present more spectra of different beams. Here's beryllium 7 beam. Here helium 6 beam. And you see the difference if you use gold target. Gold target just scatters the secondary beam. So you just see what you have in the secondary beam. And we see that the beam is contaminated, of course, because this is a feature of this in-flight method. You always have some contamination in the beam. And contamination comes mainly from the primary beam, so you have a peak corresponding to lithium 7 2+ state. You have helium 6, which is the beam that you are interested in, but you have also helium 4 and the light particles. So when you put the same beam with a beryllium target, you see that there is this long tail of alpha particles that are produced in reactions between these 2 nuclei. So this is a different spectrum of beryllium 7. So this is what we call a cocktail beam. So your beam is contaminated. You don't have only one particle, you have several particles. Of course, this is a disadvantage, but it can be also considered as an advantage, because if you are interested in elastic scattering measurements, you have several projectiles in the same beam. So you have several angular distributions that you can measure at once. This is an example of the angular distribution obtained for the beryllium 7 plus beryllium 9 scattering. So it corresponds to this spectrum here. So here, the beryllium 7 is the beam. So if you detect the beryllium 7 at 4 angles, you have an elastic scattering at 4 angles, angular distribution. But if you detect the beryllium 9 at 4 angles, you have the corresponding scattering at the backward angles. Then this is what you see here. So these are the data, and the solid curve is an optical model calculation. You see that optical model predicts as a very low cross-section for backward angles, whereas you see a very high, we measure a high cross-section. So this high cross-section corresponds to the effect of the 2 neutron transfer action. So the beam, beryllium 7, picks up 2 neutrons from the beryllium 9 and becomes a beryllium 9, and it's detected at 4 angles, which corresponds to the backward angle. So this is a transfer action. It's a two-neutron transfer action. So this is very interesting because the magnitude of this cross-section basically defines the spectroscopic factor, two-neutron spectroscopic factor in beryllium. So here I present everything I show so far was in the scattering chamber in between the two solenoids. If you go to the scattering chamber after the second solenoid, you gain an additional purification of the secondary beam. And this is what you see here. This is, you can use a degrader, a foil of some material in the central chamber, and then you make a second selection with the second solenoid, and then you see what happened. Here is without degrader, so you see the lithiumate beam and the contaminations. And here with the degrader, you can get a much poorer beam. So now I'll talk a little bit about the instrumentations that we use in the secondary chamber number 3 after the second solenoid. So this is a picture of the end of the system, and this is the last tube. This is a turbo pump, and this is the chamber. See, this is a lateral view, so you see that this chamber has 72 centimeters diameter. And inside the chamber, we have 2 rotating plates, can rotate independently, so as you can mount detectors in several combinations and rotate them independently. So the idea is to make coincidence measurements using the system. These are the plates, these are supports for the telescopes, and this is the target, and this is a plate in front of the beam. The beam comes from this side. So this is the kind of detector that we are using, simple single silicon detectors. And the connectors is microdot connectors that you use for the signals, and this is a kind of signal that we have. One problem that we have is the noise. Noise is a big problem. And we found out that a big part of this noise comes from the turbo pump controller. So we were able to solve this by putting a transformer between the pump and the controller. So these are the detectors that we use as silicon detector, as I said. The thickness, so the delta is, they are very thin, 50 microns or 25 microns, and the E's are thick, about 1,000 microns. And the areas of the detectors range between 150 and 300 square millimeters. So this is outside the chamber, the kind of electronics that we use. Sorry. This is outside the chamber. So we use this Mesitech box, which is a compact electronics. And we are able to mount up to 4 telescopes, which means 8 detectors. These are some results of measurements in the secondary scattering chamber. So these are the reactions that we measure. So here I present results for using, this is resonant scattering measurement. We have this beam, secondary beam of exotic particles like helium-6 or lithium-8, which we impinge in a target, which we call thick target, is a foil of polyethylene, thick, sufficiently thick to stop the primary beam. So the primary beam stops in this foil. Alinka told about that. And we detect the protons that recoil at 0 degrees or forward angles detectors. So the foil stops the beam, but not the light particles like protons. So by detecting the protons, we are able to have an excitation function of the collision between the projectile and the target, which is proton in this case. So these are the kind of spectrum that we get. At 0 degrees, you can see that we still have contaminations. These alpha particles are contaminations. And you have the tritons, deuterons, and protons very well separated. If you go to larger angle, you get a cleaner spectrum. This is another reaction that we performed also in the last scattering chamber, which is using a helium-6 beam on a heavy target, a 120 tin target. And this is the delta E spectrum. And you see here, this spot is the helium-6 elastically scattered in the target. And below this helium-6, there is an alpha particle, a helium-4 strip, which are particles that are produced in this collision here by some kind of mechanism, reaction mechanism that we will discuss further. So what we have here is the elastic scattering. The particle helium-6 comes here, scatters in the tin target, and goes to the detector. So I have this helium-6 peak here. But you also can have other kind of process, such as elastic breakup. Elastic breakup, the helium-6 comes, interacts with the target, and breaks up in an alpha particle and 2 neutrons. So the neutrons we don't detect, but the alpha particle we detect. And this is what we see here. So elastic breakup means that this process occurs and leaves the target in its ground state. So there is no excitation of the target. However, you can imagine a different process producing alpha particles. You can imagine that the helium-6 comes and transfers 1 or 2 neutrons to the target, and you have still this alpha particle, which goes to the detector. So these events also come from this kind of process, which we call transfer. So there is a list of names here. These are names of the same process, which is this one. Neutron transfer to continuum, incomplete fusion, non-elastic breakup, inclusive breakup. These are all names for the same process, which is this one. So you produce an alpha particle, but you leave the target here very excited. So I'll show it in the next. So the idea is the following. Which kind of mechanism you have here? So then you have the projectile, which is helium-6 in its ground state. It's a lower bound projectile, so you need very low energy to break it. And you have the target, which is the 120 tin. So the transfer reaction, you can imagine, occurs when the 2 neutrons go to the target. If you calculate the probability that this transfer occurs to the ground state of the target, you see that it's very small. It's almost negligible. And this probability is increasing as you go up in excitation energy of the residual nuclei. And it reaches a maximum more or less in this excitation energy, which is about almost 15 MeV. So it means that the transfer process is not a transfer that occurs to all final states, but it is very selective in terms of excitation energy, being much more probable for high excitation energies. So the idea is that if you have a transfer, you should leave your residual nuclei in a very excited state. So there is a formula which was developed by Brink, which describes these matching conditions which maximize the transfer processes. This simple formula here. And for neutral transfer, in general, the optimum Q value, optimum means maximum transfer probability, occurs for Q value around 0. However, for a breakup, the Q value is negative. So one would expect the energies of the alpha particles to be smaller for breakup than for transfer. So in principle, it's possible to disentangle the two processes. So here is the results, experimental results. So here in the left side, I plot the probabilities of the alpha particles, the cross-section, as a function of the alpha particle energy. It's basically the projection of that bump that I show you with the alpha particles for different incident energies. And you see that this is located more or less where around the Q window expected for the transfer. On the other side, if you calculate the breakup probability, which is done by the CDCC calculation here, you see that the prediction for the breakup lies well below the maximum of the experimental yield. So prediction for breakup is not very much reproducing what we see here. However, the transfer to continuum calculation is reproducing very well, either in the energy or in the magnitude of the cross-section. Note that the CDC has to be multiplied by 5 here. So CDC prediction is much smaller than what we are measuring, in fact. We measure much more alphas than predicted by CDC. If you change the energy, you see that this experimental distribution shifts to the left a little bit, but still the transfer to continuum is describing reasonably well the results. Here is the angular distribution corresponds to these events here. And also the magnitude of the cross-section is much better reproduced by the blue line, which is the transfer to continuum. CDCC doesn't account for the observed cross-section. Here we extend the measurements to higher energies. And we plot here the distributions as a function of the alpha particle energies. And here we transform it to the key value of this transfer action. And we see this interesting behavior. As the energy increases, the centroid of the distributions go to the left, to negative Q values. And the magnitude of the cross-sections are here. It's still very high, much higher than predicted by CDCC. So using the Brink formula, you can make an exercise here. I say an exercise because we just applied the formula to obtain the angular momentum. You see that in order to be a transfer, it's necessary that the angular momentum of the final states also increases as the energy increases. And the relation is like a quantum rotating system. Okay, now I'll talk about different experiments that are in progress in RIBRAS. So here I put a list of projectiles that we are studying. Helium-6, lithium-8, boron-8 is a candidate of proton halo, beryllium-7, boron-12. And the targets, we have a list of 5 targets which are the most normal targets that we use. Is beryllium-9, carbon-12, aluminum-27, nickel-58, tin 120, and a gold target that you use for normalization. And you see that you have light targets, medium mass targets, and the heavy targets. And the idea is to change the target in order to study the interplay between Coulomb and nuclear interaction. So for light targets, normally we are well above the Coulomb barrier. Then we are sensitive to nuclear effects. But if you go to heavy targets, the Z is much bigger, and then you have this Coulomb repulsion, and then the Coulomb interaction becomes important. So it's possible by changing the target to study the interplay between Coulomb and nuclear interaction. So this elastic scattering provides information of the nuclear potential and also the total reaction cross-section. So all the flux that comes out from the elastic scattering goes to some reaction channel. So by measuring elastic scattering angular distribution, you are able to obtain the total reaction cross-section. And inelastic scattering provides information about nuclear deformations and transfer actions about spectroscopic factors. In addition, we have this new breakup and fusion reactions, which are also very important in these exotic projectiles. So I'll be back to a problem of instrumentation. RIBRAS has some problems. One of the problems is the residual magnetic field around the solenoids, which prevents the use of detectors based in electrocollection, such as vacuum tubes in the old photomultiplier, or gas detectors such as ionization chamber and proportional counters. So this limits the number, the kind of detector that you can use in RIBRAS. And there is also a strong secondary neutron beam coming from the primary target. So it prevents the use of germanium detectors. So it's difficult to measure other observables other than the charged particles, such as gammas and neutrons. We are presently mounting a system to measure gammas. So as I said, gamma is not easy to measure, but nowadays there is a new kind of scintillator, which is LISO scintillator. It's a crystal which is not sensitive to magnetic field, so it can be used in the magnetic field of RIBRAS. So the idea is to use these LISO crystals to detect the gammas together with particle detectors and make coincidence gamma particles. So we did an experiment. This is a photo of the experimental setup. Here we have four telescopes mounted here for particles. And around the target is here. Around the target you have four LISO crystals, small LISO crystals to detect the gammas. The beam comes from here. And the beam was litinate and target in 120. And we measure a nice type peak. TAC means the time, events in coincidence, gamma and particles in coincidence. And this is a spectrum for the particle detector. So we are able to look the gammas that are in coincidence with litinate and the gammas which are in coincidence with other particles, light particles like alpha particles. And so the gammas in coincidence with litinate should correspond to inelastic excitation of litinate, which is very interesting. The gamma in coincidence with light particles should come from fusion, which is also very interesting. So it seems this was a first experiment, but I think it's very promising. More experiments that we are doing is, for instance, we are doing boron 8 plus beryllium 7. So the idea is to measure, when you collide boron 8 with beryllium 9, you have a very exotic system. So boron 8 is very weakly bound, only 137 keV, binding energy. And beryllium-9 is also equally bound nuclei. When you collide these two nuclei, you form fluorine-17, which is a proton-rich nucleus, which will decay mainly by emitting protons. So the idea is to measure the process distributions from this reaction. Other elastic scattering that we are doing is lithium-8 with several targets. Lithium-8 is A equal to 8 nuclei. There are no stable nuclei with mass 8. So this is a gap in the nucleosynthesis, Big Bang nucleosynthesis. A equal to 5 and A equal to 6, to 8. There is this gap. So there are two bound nuclei with mass 8, lithium-8 and boron-8. So with this kind of measurement, we can study the nuclear potential of A equal to 8. And also to neutron transfer reactions. So future setups, we are mounting a system of two double-sided silicon strip detectors. These are large detectors. This is 5 centimeter by 5 centimeter. And they are strip detectors, so they are able to obtain the XY position of the particle. So this kind of detector is a large area, so it's very suitable to be used with secondary beams, which are low intensity, and are very, very good to make coincidence measurements. So we are mounting the system, and the system is being tested in a beam line just beside RIBRAS using stable beams, and then to be back to RIBRAS. And we also have this neutron wall in the laboratory that I will not go into details here, but in principle, we could use it to measure neutrons, which would be very interesting. So this is the RIBRAS collaboration, and thank you for your attention.
Thank you so much. Questions, comments? No question? Then thank you very much again, and maybe coffee time. And next talk is Professor Mauro Cosentino, Federal University of ABC. Title of the talk is Simulation for High Energy Physics Detectors.
Torrieri.
Oh, okay.
Yes. So where's the laser here? Is it the top is the laser? Oh, it's like this. Yeah, okay. Luckily, I was not pointing to my eye, right? So, okay, the presentation, the title of my presentation may sound a little bit more ambitious than it really is shown. So, basically, what I'm going to provide you is a general view of detector simulation and a little bit more oriented to gaseous detectors. So I will speak a little bit of the motivation, and then I will then speak about a little bit of the simulations itself. What are the main techniques of general simulations for this kind of detectors? The physics processes, or what they mean in terms of simulations. What does it mean, a physics process in a simulation? And then the main tools that we are using. GN4 and Garfield++. And then we go to gaseous detectors. I'm going to explain a little bit more in detail of the principles, the working principles that gaseous detector has, and how this affects the simulation. So it will be a little bit, some of the conditions or of the characteristics of gaseous detectors will be talked about earlier than the working principle, but they will be explained in more detail later. And this is needed so that we can understand how the working principle, or understanding how the working principle of the detectors and the way the simulators are done, what are the constraints that you need to fulfill in order to have a meaningful simulation. And then I finish with some prospects. So we are considering to propose, so there is a upgrade proposal for the ALICE collaboration, which is a forward calorimeter. And one of the components of this forward calorimeter is an hadronic part calorimeter, which we are considering to make a proposal, the Brazilian team, not myself only, but the Brazilian team. And I will present details of this idea. It's still a very rough idea. And I will talk a little bit about the prospect of gem detector in PANDA. So now I see why everybody comes in here, because it's really hard to read. So there are several high energy projects going on and to be started. So there are many more than fits in a slide. So there is in the future the linear collider, which is precision Higgs measurement beyond standard model, etc. The ongoing superpower LHC, which has detected the Higgs and still working on understanding the Higgs properties. The search for beyond standard model physics, heavy ion, where I'm working with, and there's also CPT or CTP, depends on how you prefer to speak the symmetries. And then fair physics, we are all here. I don't dare to go in deep on that, because there are much more people that have been explaining much better than I can. So basically, we have some interests in here too. So there may be some antiproton on heavy ion, so this can be interesting for us. And there are many others. So there are RIC, so Marco spoke this morning about the migration of the São Paulo group from low energy physics to high energy physics, and everything started with the STAR experiment and the RIC. So this is where I also started when doing my PhD in STAR. And there are also other good facilities around the world working so far. And they all have, or they may have, or they can have, at least one experiment with gaseous detector, right? So this is the main physics and project motivation that I see, that there are applications for what I'm speaking here. So many of these projects use or can use gaseous detectors for tracking, muon detection, charged particle veto. So this basically is just some sort of layer of detector that says, look, there is a charged particle going on. Normally you want to measure photons, for example, and you need to know if the signal that you have in your calorimeter is not coming from an electron, for example. So then you need a charged particle veto. And in calorimetry. So calorimetry, what is a calorimeter is, okay, let's go on. I will speak about calorimeters later for those that are not acquainted to it. So tracking, there are several ways of doing tracking. There are several kinds of detectors. There's the drifted chambers, the time projection chambers, the muon tracking chambers, the straw tubes like we saw this morning. And this is a picture of one lead-lead central event in the ALICE experiment. So this lots of spaghetti things are just the tracking of individual charged particles. So this has a multiplicity of higher than 2,000 charged particles in here. So this is a huge volume gas, so it's almost half the size of this, or half the size of this auditorium. And so this is one of the examples of what can be done in a high energy physics environment. So the other kind of detection is for muons. For example, in the LHCb, so they have these muon chambers here. So basically what they do is that they have several chambers, one after the other, and then they can do the tracking as the track of the muons go here. And so what is different from here to here is the difference is that there is a lot of material in front of the muon detector, right? So most of the hadrons and all the other charged particles will stop before arriving here. The only thing that we expected to go through all this material are the muons. So if ever you see any signal in here, it must come from a muon, right? So this is why, in general, when you see muon detectors, they are the last one in a scale, right? So you have several stuff in the middle. So you have tracking, you have calorimetry, you have coils for magnetic field or whatever, and then you have these guys, right? And CPV intends to improve photon PID. Normally, this is what they want. And it's normally associated with a calorimetry system, right? So you do the calorimetry to detect the photons, and then you have to have something else in front of it so that you know that the signal that you're watching to is not actually an electron or something else. Of course, if you have a detector like ALICE, or if you have a detector like CMS, where you have a tracking system in front of it, this is not very important, but this is the CPV from the ALICE experiment for the FOSS experiment, which is a smaller size calorimeter with higher energy resolution. And after years of working with the ALICE tracking, they realized that it could be better to have a dedicated CPV really close to the surface of the calorimeter, because you have to rely in algorithms that will make the propagation of the track through the calorimeter. So there is a space where you don't know what is going on. You don't have tracking in that space. So you may not know if you're really matching the right charged particle track to the right calorimeter signal. So this is why you put something like that very close to your calorimeter. So calorimetry, what is a calorimetry? What is a calorimeter? So calorimetry is a technique where you destroy the particle, right? So the particle will not go through the calorimeter anymore. When you do a calorimeter, you expect that the particle will end here, will die here, and leave all its energy there. So the name calorimeter is in association with the energy that you have in a typical classical calorimeter. So you have the energy contained inside some hermetic volume, hermetically closed volume. So here the idea is the same. So you have the particle goes in and makes a flash of energy and dies there. All the energy is deposited in this calorimeter. So basically, one of the things that you can do with gaseous detectors, you can have here several layers of lead and scintillator. And then at some point, what you do, you put a gaseous detector that has a higher granularity on position of the tracking of the charged particles. So what happens here is that if you look, so these are in inverted directions, but this is the electromagnetic calorimeter star. So what you have is, you have, for example, an electron coming here or a photon coming from below. It hits here, it starts developing a shower, and then the shower gets larger and larger, and then here you have the maximum amount of energy deposition. So this is where you put your your sensitive gaseous detector, because there you will have the maximum amount of charged particles that you can detect in here, right? And this is schematically what is happening in there. So you have the showers developing here. This dashed volume is this first section here, the several lead and scintillator layers. So it's just a volume of something that is making the shower develops. And then at some point, the shower is here and makes the signal in the gas, and then you have the readout. And then the readout gives you X and Y position so that you can see the size of this shower, right? And why you need to know the shower? Because if you have a hadron, for example, if you want to distinguish between a pion and an electron, the pion will not make something like that. It will just make a minimal ionization. It will go through. It will make just a dot. You will not have area of shower. Okay, so now we jump to simulation. So we have several possibilities of gaseous detectors, and then we have to simulate. So here I'll give you some basic general information of how simulation works for simulation detectors. So in general, there are several, right? There's not only one. We saw in Tobias' presentation in this morning that we had at least 4 PANDA. They have GN3, GN4, and maybe in the future they also will have FLUCA when they fix the problem with the license. Yes, and then, so you have several, right? So they are basically called the Monte Carlo radiation transport codes. So you can choose the one that fits best for your experiment or for your own experience, right, with coding or whatever you do. But they all rely on basically the same kind of procedures, the same techniques, and etc., right? So they all model an apparatus in terms of elementary geometrical objects. So you make a big thing made out of various small elements. And they have lists of physics processes which are model dependent. So you have an electromagnetic process that is going on in your detector. You have a hadronic process that is going on in your detector. Any of them, you may have several hadronic processes. You may have several electromagnetic processes, Compton scattering, pair production, whatever. This will always rely on some sort of model. And particles so you simulate an incident particle. So let's say you have a proton-proton collision or an anti-proton-proton collision. You have several tracks, right? So your simulation will take each one of these tracks and will propagate it through your detector, but they will do it one at a time. So you take the first pion and goes until this pion dies or disappears from your detector. And each one of these transports will treat it in steps. And this is important because this is basically the idea of what happens, right? So you have the starting point. You divide your detector volume and material in steps. So the size of each step will depend on the process that you have turned on. So you may not turn on, for example, Compton scattering. So you may have a calorimeter that there's no Compton scattering. Is it meaningful? Depending on the energy, yes, because you know that the photoelectromagnetic, the electromagnetic processes depends, or the interaction of the photons with matter depends a lot on the energy. So for very high energy photons or very high energy electrons, you may not have Compton scattering at all, right? So what happens here is that it will calculate the size of this step depending on the cross-sections of the processes that you have turned on. So if you have one cross-section higher than the other, it's more likely that you will have one or the other. So you have a Monte Carlo, it will make a sampling, and then you randomly will choose, but this random will be weighed. This distribution will be proportional to the cross-section of each of the processes. So the size of the step will depend on that. And most of the time, what you have is, most of these detectors, these transport detectors, will do the following. Once you have, for example, here you have a layer of your calorimeter or something like that. And here you have another layer. And you have modeled in your simulation the several layers of your detector. When it sees, when the code sees that there is a boundary here, it will stop the tracking here and will start another step. So even if the cross-section of the material would say, okay, you could go all the way down here, it will stop at every boundary that it finds. So why I'm saying that? Because the more granularity you have in your calorimeter, the slower it will be your simulation, because the amount of steps is the one that, the number of steps is the magnitude, is the number that will determine the speed of your simulation, right? So if you put lots of processes, tiny Columbus scatterings, etc., you have several short steps, and this simulation may last forever, right? So it will not be ready in a human time life, right? Even if you parallelize. So for each step, what happens is that length is determined by the cross-section of the processes. If there are secondaries, they are added to the list of particles, right? So we start, let's say, with 10 particles coming from the original collision. And then one of the particles, let's say it was a photon, it creates a pair, an electron and a positron. This electron and positron will be added to the list and will be treated later, right? And for each step, it will also calculate the local energy deposit, and this process is over when the particle is destroyed by the interaction. Let's say the photon was destroyed, right? So you have a photon, it creates a pair, electron-positron, and then it dies. There is no more photon. So it stops for that photon, right? Or it reaches the end of the detector. So the detector ends here, you have your collision going here, and it goes, there's no point of simulating it after, right? So it stops for that particle. And the energy is below some sort of tracking threshold. And this is the tricky part. Okay. I think I'll go back to talk about this later, the problem of the tracking threshold. So let's say that I will just make I don't remember now if I put this in the future. So if you have, for example, if you set this threshold at some energy higher, for example, than 1.2 MeV, then you may not see pair creations at that energy, right? You may not see a pair creation at lower energies. You may see a pair creation if you have a photon of 20 GeV, but you may not see any pair creation below, I don't know, 100 MeV. This is useful because you want to make a fast simulation sometimes, but of course your response will not be very realistic, right? So this, we have to be careful when tuning this thing. So after the simulation for the particle is over, it yields as outputs new particles created, so it's an indirect output, so the electron pair, for example, electron-positron pair, and local energy deposited through the detector. This is some information that is associated directly to the particle. And then the local energy deposits along the sensitive parts of the detector can be digitized, as Tobias has shown here in this morning. So this part, most of the detectors, most of the simulators, they don't go in there. They let, so Fluka, Gian4, Gian3, whatever, they come up to this point. And then you're on your own. You do in your experiment whatever it's best for you. And then the idea is that you take the electric current or voltage signals and treat the same way as you would treat in your reconstruction chain, right? So, but this is up to the user, right? So this is through PandaRoot, it's through AliRoot or something else. And then, again, there's a trade-off between accuracy and speed. So the more accurate you want, the slower it will be. And the faster you want, the less accurate it will be. So more precise physical models are slower and, more importantly, create more secondaries and more steps. And also tracking and production cuts, you can choose how much. There are two things that can slow or speed up, is the model that you use and the thresholds that I just mentioned, right? So if you put standard cuts, for example, you may make a detector simulation, gaseous detector simulation impossible, because you have the ionizations are in the range of electron volt, and the standard cuts are on the range of tens of kilo electron volts. So then I start looking why I use GN4. So because GN4 is one of the most widely toolkit used in high energy physics community. So there are lots of people that use. It's very well tested. You know a lot of this. So this is important. Someone has validated a lot of things for you. Because it's written in C++, and this allows for modularity of physics modules, and as an object-oriented language, it allows you to manipulate several objects as you wish. And you can, of course, you can plug in models, different models that you want for different processes, etc. And also because it's multi-threadable. This is very important nowadays to speed up your simulations. And also, GN4 can be used to define the geometry, the materials, and the physics process. So you may simulate your own trigger primary particle. So you have this particle gun that is inbuilt in the GN4. So if you want to test a given block of whatever material you are testing, and you just want to throw a pion in that, so you can do it. You just go there and choose, throw a 50 GV pi plus there, and let me see what happens. It gives position, time, size, and kind of the primary particle ionization. But for gaseous detectors, charge multiplication is not well performed by GN4. We need something else to transport the electrons and make the multiplication. And this is where we started using Garfield++. So Garfield++ is an electron transport and multiplication simulation toolkit. So it's basically aimed to simulate what happens once you have the electron in the detector. It doesn't care about how the electron got there in the first place. But once it is there, it does the remaining part very well. And also has a built-in interface to root analysis toolkit. So it's very easy to analyze what you have there later on. So to summarize the two tools, so GN4 does not simulate avalanches very well. What are the multiplications? And Garfield++ does not simulate the initial interaction very well. So the strategy is to simulate the ionizations with the GN4 and then use Garfield for the transport and the avalanche. So the working principle of the gaseous detectors is that is basically for charged particle detection. Charged particle ionizes the gas, which is submitted to an applied electric field. So the electron goes in one direction, the ion goes in the other direction, the electrons goes very fast, and the ion goes very slow. So the electron and ion drift in different directions. Electrons are attracted to a very steep potential well. This is normally how we do it. You take the electrons and you put them in a trap where you multiply them through multiple scatterings. So they will collide to several ions of several atoms of the gas. We will ionize all of them, and all these electrons, these new electrons, will fall in the same potential well, and they go in the same direction, and they will be accelerated and create secondary, and so on. So this is what is called avalanche. So this is the typical situation where you have spread over avalanche. So it's one of the simplest, or the simplest gaseous detector, the Geiger-Müller tube. So basically what you do, you have, this is cross-section longitudinal cut, right? So this is like a cylinder with a wire in the center of the cylinder. And here you have the anode wire, and here you have the cathode cylinder. You have a potential difference here. You have this cylindrical symmetry of the electric field, which makes, at some point, the gradient very high, and this will make the electrons to acquire very high kinetic energy, and then they will start. So you have a charged particle going on. It creates an initial electron. This electron we will drag down. It will start to multiply. It will get enough kinetic energy here. It will ionize another ion, and the electron created here will ionize another one, and so on and so on. But then, here it's in a configuration that when this happens in the gas in this process emits ultraviolet photons, and these ultraviolet photons create secondary electrons here and here and here, and then you have the avalanche all over the wire. And this is not very useful for example, energy measurements. So you want the proportional regime to make this energy measurement. So basically, it's the same thing as the Geiger-Müller tube, but you change some of the settings, the composition of the gas, for example, the intensity of the fields. And then what you have is that you have a response of the signal that is proportional to the energy that was deposited in your detector, right? So this is the main principle of the very used multi-wire proportional chambers. You have several wires, such as the Geiger-Müller tube, put in series in an array, one on the other side, and then they allow to determine the position of the ionization processes. So this allows you for doing tracking. And these are the multi-wire proportional chambers are the traditional macro pattern detectors, and nowadays, or since the last 20 years, the field is moving towards to micro pattern gaseous detectors. And there are several. I will not speak about all of them. I will talk only about the GEM, or gas electron multipliers, which is the avalanches happen in microscopic scale. So this is a GEM foil. So it has this shape when you look in a cross-section area. There's this biconical shape. So a cone here and a cone here. This is biconical shape. You have a conducting material here, and here you have an isolating material. What you have here, look, the dimensions here are very small, 70 microns, 55 microns. And you have this very intense electric field here. And once the electrons are dragged in here, they start multiplying, and they create a cloud of electrons here. And then one thing that we can do is to associate several of these foils. So you will have the electrons that were the output of the first multiplication will be the input of the next multiplication. And this will increase the gain. The other nice side effect of this is that this will reduce the ion backflow, which is very important for detectors such as a TPC. So you don't want that the ions that are created during the process of a multiplication, you don't want them to go back to the drifty area of your detector. So you want them to be trapped around here. So some of them will go to this place, to the conducting here, to the conducting material here. But if you have several layers, the ones that are produced here, they will go here and they will die. So they will not be going through the active area of your detector. So it's not going to ruin your signal. And also these are faster, these detectors are faster than the typical multi-wire chamber, because the signal in the multi-wire chamber are basically from the drift of the ions that is very slow. So it's a process that happens on a microsecond scale. And here what you have is that once you have finishing your multiplication, you take all the electrons that you have created, and you induce the signal in nanoseconds, right? So it's very fast. So one thing that you can do, you can use these thick gems. What are thick gems? Thick gems, Marco has talked about. Thick gems are gems more robust. They are thicker, they have thicker material, they are bigger in thickness, and also the holes are wider too, right? So it's not very difficult to build. They are easier to build. And also because of that, they are cheaper and they are more robust. So depending on the application you want, it's better to have a thick gem than a gem because the gems, they break very easily. The problem with that is that you probably will have a higher ion backflow because the holes are bigger, so it's more open to the backflow, and it's less performing than the gems, but depending on your application, this may be just what you need. And okay, so the physics, the simulation constraints, so once you know how the detector, the gaseous detectors work, you have to remember how the simulations work. So you have the problem of generating the primary signal in a gaseous detector. This primary electron, when you have a charged particle going on and ionizes the gas and makes the first electron that will be multiplied, that will make the avalanche, it happens in a EV scale. And the simulation normally has a threshold cut on the tens of keV. So you will never see any signal in your detector if you do the simulation as it comes from out of the box, right? So you have to lower the threshold, but lowering the threshold comes with a cost of computing time, okay? Maybe several orders of magnitude higher. So the challenge here is to have a realistic ionization within a physical computing time. So the prospects, one of the prospects that we have, that's one of the ideas that I was telling you in the beginning. So the hadronic calorimeter for the focal. What is the physics motivation? So the focal wants to probe the gluon saturation and maybe confirm or reject color glass condensate. And these effects are enhanced forward rapidities, right? So the ideal probe for the calorimeter are direct photons. So you need somehow to know that what is coming through your detector is a photon. And the issue is that the focal is completely outside of the barrel, so there is no tracking in front of it. So one of the things that we also have thought about is to put a thick gem in front of the electromagnetic calorimeter to use it as a charged particle veto. But then this idea is more interesting of a project. And why we would need a hadronic calorimeter? Because one of the things that you need, one of the techniques that you may use to detect the direct photons is to use the isolation method, right? So if you have a direct photon, you should see no signal in, where is the pointer? You should see no signal in this detector. So basically, this detector, this hadronic calorimeter, the idea is, so we have a sampling calorimeter, we have lead layers intervalled with thick gems. So here is where we will detect the shower parts. So of course, you see there's some loss here when there's some energy lost in the lead layers. And as a project motivation, the hadronic calorimeter, based on thick gems, is one of the things is that the thick gems are normally in big areas, in big area detectors, cheaper than scintillators that work with avalanche photodiode or silicon photomultipliers. The readout pads of 1 centimeter by 1 centimeter approximately allows for digital calorimetry, which means that you can, instead of measuring the energy directly, you can count the number of signals that you have. And since you have this digital calorimetry feature, this allows us to have a detector that is consistent with particle flow algorithms, right? Will become the standard way of doing analysis. And also there's our rising star, the sample chip, that is already there, and then we can just use it as the readout electronics. This is some of the things. I think that Marco has shown something similar to this one. This is one of the things that we have already done here in São Paulo. So this part is being tested for a while right now. And this is a simulation that we have done in our institution based on this detector. So this is the kind of thing that we are doing. So here are the individual electrons. So here are these dark spots are the holes of the thick gem where the multiplication is happening. And here are the avalanches being collected in the readout system. And just to, it's not really something for a PANDA, but it was inspired in PANDA. So I asked my students so they could do TPC for PANDA. And this is what we got. So this is what they did since, I don't know, I asked them to do it on Friday. So it was finished yesterday. So, and all of us, we realized how challenging it is just to make one. This is we are simulating actually cosmic rays. So the blue line is a positive muon coming from the sky, right? And the red straight lines are the electrons that are being propagated in the gas due to the electric field. So this is just one appetizer of what we are aiming to do. And okay, so conclusions, detector simulation is a business on its own right. Lots of physics processes to be understood, model, etc. It's a team effort. Manpower is crucial. Well-trained manpower in principle is crucial. And is an essential effort. So the physics in the end is the main goal. Everybody wants to know if there are the glue balls. I also want to see the glue balls. But we can't get there without the simulations first. So this is what I wanted to show you today. Thank you very much.
Thank you very much for the talk. Questions, comments?
Yeah, thank you for this nice presentation, and I strongly support your last slide. I just want to mention that there's a new feature in PandaRoot implemented now that if you get to a volume which is very difficult to propagate through, like a calorimeter, they have now the possibility to switch off Géant 3 or 4 inside this volume, and then you could use whatever you want to propagate in that. And there are efforts going on at LHC to use recurrent neural networks to mimic the behavior of an EMC when it certain particle types hits that, so that you can make a somehow fast simulation to get really a faster answer, and this simulation process doesn't take so long. So it's really a very interesting and very important topic.
Yeah.
That one gets it faster than it is at the moment.
Yeah, so 2 weeks ago we had this GN4 workshop here. So the people from the GN4 team came to, and they barely told something similar to that. And they said also they have a feature that you can, for example, you can say that here you want the simplest simulation as you want, just to make the more easiest thing. And then in these thin pieces of gas, then you do your magic. You put whatever you want there, and then you have a compromise. So basically, it's in the same idea. Thanks for the comment.
Other questions, comments? Probably coffee time. You can ask. And okay. We start 4:40. Come on, coffee time.
Thank you.
Thank you very much again.